Welcome back, everyone. This explainer is brought to you by Forge College. Now, if you caught our last session, you know we got deep into the weeds on theoretical transaction forwarding patterns. Well, today we are taking all that high-level Gulfstream theory and turning it into a concrete, actionable strategy. Think of it like taking those raw engineering blueprints and finally pouring the foundation. We're bridging the gap between how transactions are routed in theory and what that actually does to network performance in the real world. So settle in, we're going to break down some heavy Web3 mechanics, and we're going to do it with some really cool minimalist, patent-style diagrams today to keep everything crystal clear. Let's get to it.
Okay, let's dive into this. Here is our blueprint for today. 1. Welcome to the mailroom. 2. The great transaction race. 3. Comparing forwarding approaches. 4. The 3 strategy knobs. And finally, 5. Synthesis and next steps.
Starting right off with Section 1, welcome to the mailroom, where we'll be visualizing the mempool. To really wrap our heads around Gulfstream, I want you to picture a massively fast-paced, highly organized corporate mailroom. In a standard mempool, clients just dump all their letters into one giant box, and the boss, the network leader, has to sort through the whole pile alone. But our distributed mailroom model, it totally flips the script. You hand your letter directly to the clerks, which are our validators. These clerks do the heavy lifting, pre-sorting and pre-validating everything before handing nice, neat, prioritized batches up to the boss. This completely decouples when a transaction is first seen from when it's finally ordered.
But, as you can imagine, a mailroom like this comes with its own quirks. We've got 3 main friction points to look at here. First up, visibility acquisition. Simply put, who sees which letters and when? Second is speculative processing, meaning our clerks are actually tearing open envelopes and running pre-checks on the fly. And third is ordering reconciliation, where the boss steps in to resolve conflicting batches. It's actually kind of funny when you picture it. You have these incredibly overzealous clerks racing to pre-check everything to save time. But because they aren't all looking at the exact same pile of mail, they end up handing the boss slightly different priority lists. It saves a ton of time up front for sure, but man, it creates a massive coordination headache for the boss at the end of the line.
Moving right along to Section 2, the great transaction race, or what happens when forwarding paths collide.
Now, what's really interesting about this next part is seeing a direct collision play out in real time. Look at transaction A on top. A client forwards it to validators 1 and 2, and it's trying to grab a specific scarce resource. Now, check out transaction B on the bottom. A totally different client forwards it to validators 3 and 2, trying to spend that exact same resource. Do you see the bottleneck? It's right there at validator 2. Boom! We've got a full-on race condition happening right in the middle of our mailroom.
Which brings up the million-dollar question. Who actually wins this race? Think about it. Validator 1 runs to the boss screaming, "Transaction A is good to go." But a millisecond later, Validator 3 slides in and says, "Hold up, Transaction B is ready first." So how does the network leader actually break the tie?
Well, here's the exact mechanical sequence the boss uses to sort it out. Step 1, the leader takes in all these fragmented, sometimes totally conflicting batches from our clerks. Step 2, they apply their chosen heuristics, basically the house rules. And Step 3, the leader makes the final call and locks in the transaction order. The winner is entirely up to the leader's rulebook. If the boss favors earliest arrival, well, it's blazing fast, but it definitely gives a massive edge to clients with the best network connections. On the flip side, if the boss demands a quorum, waiting for multiple clerks to agree a transaction is ready, it levels the playing field and makes things fairer. But naturally, that slows the whole operation down.
Now, we can't ignore the hidden architectural cost here, which we call state staleness. Remember those eager clerks doing all that speculative processing? Well, what happens if a clerk pre-approves transaction A, but transaction B manages to sneak in first and get stamped by the boss? Transaction A instantly becomes invalid because the underlying state just changed. The clerk's pre-approval gets tossed out. That means all the local CPU and memory the clerk just burned pre-checking transaction A completely wasted. And that wasted effort, right there, is the true hard cost of speculative processing.
That brings us to Section 3, comparing forwarding approaches. Let's map out these architectures.
And this brilliantly illustrates the real-world trade-offs we're dealing with. Let's scan this spec sheet. First, the leader-centric approach. Here, ordering happens purely at the leader. Latency is definitely higher, but the validator load is nice and low because the clerks aren't sweating over pre-checks. Next, validator relay. Distributed signals help pull the latency down, but suddenly your validator load jumps up to the moderate to high range. Finally, check out the Gulfstream hybrid approach at the bottom. It runs on fragmented visibility, which just crushes latency. It's super fast.
But look at the far right column, high validator load. You're demanding serious heavy lifting and heavy memory from your validators to manage all those pre-holds and speculative checks.
All right, Section 4, the 3 strategy knobs. This is where we engineer your forwarding policy.
You know, as someone learning the ropes here, you aren't just watching from the sidelines. You're an engineer. And to get the precise system outcomes you want, you basically have 3 main dials or knobs on your control panel. Knob 1 is fan out. Simply, how many clerks even get the letter in the first place? Knob 2 is speculative depth. How many checks and how intense are the checks that the clerks run before passing it up the chain? And knob 3 is the reconciliation policy. What is the boss's exact formula for breaking ties? By tweaking these 3 dials, you are literally engineering the trade-offs between latency, stability, and system load.
Let's put this into practice and contrast 2 totally different strategies. Say your ultimate goal is blazing fast latency. Maybe you're dealing with high-frequency trading. You're going to crank that fan-out dial all the way up so everyone sees it instantly. You'll keep your speculative checks shallow to save time, and you just accept that ordering might get a little chaotic. You just need it fast. But what if your goal is rock-solid stability? Like for predictable DeFi primitives, you do the exact opposite. You turn the fan-out way down. Demand incredibly deep, thorough checks from your clerks, and require a strict multi-validator quorum before the boss commits anything. 2 completely different goals, totally achieved just by tuning those same 3 mechanical knobs.
And we've made it to Section 5, Synthesis and Next Steps, where we anchor your design thinking.
So, let's pull all this theory together into 2 absolute, foundational principles that you need to memorize. Here is Principle 1. Forwarding changes where and when visibility appears, but it does not automatically change ultimate ordering authority. So the crucial point is this, and it doesn't matter how much sorting your clerks do or how insanely complex their pre-checks get, the boss always finalizes the sequence. Provisional readiness from a validator is not the same thing as definitive ordering.
And here is Principle 2. Every reduction in leader critical path latency corresponds to an increase in validator responsibilities or reconciliation complexity. Listen, there is absolutely no free lunch in system architecture. Any latency gains you manage to squeeze out, that is a strict budget, and you pay for it with validator CPU, memory, and network friction. You've got to allocate that budget intentionally, based on exactly what you want your network to do.
So where do we go from here? Next up is the principles of transaction forwarding protocols. In our next explainer, we're going to take all these qualitative, slightly chaotic mailroom concepts we just walked through, and we're going to translate them into formal, rigorous, and measurable metrics.
Before we wrap up, I want to leave you with this provocative engineering question. How will you tune your system's dials for latency versus stability? Seriously, think deeply about what your specific network needs to prioritize. Thanks so much for joining me today. Keep exploring, keep engineering, and remember to head over to forge.college to learn more about this subject, continue your track, and dive into even more Web3 topics. This explainer was made by Forge College. Until next time, keep those transactions flowing.